Assalamualaikum warahmatullahi wabarakatuh and good day. In this video, basically, I want to discuss the mass moment of inertia, the subtopic that I have recorded in, the first early video, because some of you have asked me, sometimes, sir, why sometimes we have, how, sometimes we have to use, for the example, IO, IG. Sometimes we found that, for example, IG plus md square, and then sometimes IG plus mr square, and so on and so forth. Sometimes we got confused. Sometimes how we are going to choose this kind of mass moment of inertia. But before I explain, based on the figures in this video, two figures here. First one and the second one. Alright, so the equation here, basically nothing's wrong with this equation. Basically, if you understand the concept of main moment of inertia, you understand it, so whatever equation you use, you can solve it. You will get this, it will lead you to the same answers. Okay, let's discuss this example. Let's discuss this example. All right, we have a similar slender rod. The mass for both one lah, even though the size is different, but it is a similar one, identical slender rod, where the mass is 30 kilogram. For the example, it has a external moment which is 60 Newton meters. Rotate at point O. We see the first one. And omega, at this instant, omega is 6 radian per second. Okay, similar to this one. Okay, and then for the first one, it is a 0.9 meters, the length from O to point, for the example, point B. All right, from the length of this one, for the second one, similar, 0.3 plus 0.9, which is 0.9 meters. It has a external moment 60 Newton meter, similar, and additionally we have omega is 6 radian per second as well, similar. Figure number 1 and number 2 is similar in terms of weight, in terms of size, in terms of everything is similar, except the point of rotation for figure 1 is at the end, left end of the slender rod, left end. But for the figure 2, the point or axis of rotation is at point O, 0.3 from left end. Okay, a bit different. The first one at the end, left end, but the second one, its axis or point of rotation 0.3 from left end. All right. So basically, to solve this problem, basically is a rotational about a fixed axis, but the use of main moment of inertia similar to all problem, either in rotation, in translation, or in general plane motion. The concept is similar. So I divide it into two, for example. Means two figures lah. Of course, we have to draw. First, we have to identify where is the G, the point of the center of gravity. Of course, for a symmetrical rigid body like a cylinder rod like this, G is of course in the middle. G 0.45 from both ends. So G for this one is somewhere here. Okay, 0.45 from right and left end. Okay, you know G. That's the first thing. You have to know where is the G, and you have to know where is the point of rotation. Okay, or axis of rotation, of course, at point O, and here is at point O. That's the most important things, and before you go to the use the equation of motion to solve it. All right, and then okay, you have to draw first. We have to draw free body diagram for both figures. All right, for this one, what do we have? We have we have first is weight, right? Second, we have external moment. Free body diagram, anything regarding the force and moment. And then we have reaction force here. For the example, I put here OX, and I have OY. First one. For this one, we have what? Similar. We have weight in the middle. We have reaction force here at O, which is OY. And then we have OX. And we have external moment. That the FBD. Then another one, we have to draw the kinetic diagram. Anything regarding to acceleration and mass and angular acceleration. Okay, we draw it. And acceleration happen referring to G, to center of gravity. So G is here. Of course, this is a rotation, rotational motion. It will create. So the rotational motion create a counterclockwise. So you have two component of A, which is AT, and then AN. AN towards point O. Alright. And then you have another one. What? Alpha. Angular acceleration. Similar to this one. Kinetic diagram of it is you have okay, this is O, this is O, this is G. Similar thing, you have AT and AN. AN where R here I put it as a R1 from point G to O. This one I put as a R from point G to point O. Okay, similar thing, you have the alpha. So you have completed drawing the free body diagram for both figures. Okay, it's clear. It has W as moment, acceleration force at O, but the location of O is a bit different. Okay, and then you draw the kinetic diagram. You have AN, AT, alpha. Okay, if you draw the for this figure, you can draw the global coordinate system. I draw for both. I draw for both. You have X in this direction. You have Y. You see that on the disconnected diagram, AT is upward. So easily you just you draw the X the coordinate system, normal and tangential coordinate system based on direction of AN and AT. AT is upward, it's better. This one T. AN to the left, just put it to the left as a axis of N. Okay, you see that Y and T is parallel, and same direction. X and N is also parallel but opposite direction. Okay, so this both coordinate system apply to both figures. Both figures. Now, you have to come up with what? The summation of force in N. Sorry, the summation of force in X and Y for both figures. Okay. For the first figure, summation of force in X. We have X, I draw it, Y, and then we have N and T. Don't forget. Summation of f in x is equal to max. To the right is positive. Okay. You see from the previous free body diagram, we have only OX component. So OX to the right is positive, and then AX is equal to AN, because AN represent the component in X. Okay, so you have OX is positive, and instead of AX, just put AN. But AN is opposite. You see, AN to the left, AN to the left, so it gives you negative. Yeah, put its negative in front of M is okay. Okay, and summation of F in Y, in Y, positive upward, summation of F in Y is equal to MAY. So how many component of force? We have OY is positive, W is negative, and AT is upward, is also positive. So you have OY minus minus W is equal to MAT. So we know the equation of AN. AN is equal to R omega square. Okay, and AT is R alpha. Okay, so here you can make it as a M R omega square, and here is M R alpha. Okay, see, uh for the figure 2, for the figure number 2, I think it's similar lah. It's similar. To the right is positive. Summation of f in x is max. Okay, so ox is negative man, or negative m r omega square. Similar, because even the from the FBD it gives you the similar things, similar direction. Okay, and the similar component of force. It will be a problem lah. I don't want to discuss more on this. So you can use this one for solving the problems. Okay, in y as well, if MAY is equal, so OY minus W MAT, so it gives you negative MR alpha. Okay, so enough for the summation of force in x and y. And then the problem comes when you want to create another equation where the summation of moment is what? That's the problem. Summation of moment is equal to what? Okay, I will stop here. I will continue to the next video. Because if I continue with the same file of video, it will create, it's too big for you. It's too big for you. Okay. All right. So we continue to the next video, in the next video. Thank you very much. Hello guys. I think I have to proceed. I think it's better to have the same video, even though it will be so long. Otherwise you can otherwise you have to stop, look another videos, and then I think it's not so good lah. All right. Okay. Now the problem comes in when you want to find you want to create another equation, summation of moment. Okay, summation of moment is equal to what? Okay, I give you a few tips. Few tips. First, you have to know. First, you have to know the axis of rotation. Where? So O on the left side. Here is somewhere from 0.3 from left side. That's the thing. Then you have to know where is G. You have to know GG is of course, a symmetrical rigid body, G is in the middle lah. Okay, that's the most important thing you have to know. Okay, now the summation of moment, nothing to do with okay, you see here, before that, summation of moment. Sometimes you find summation of moment at G, summation of moment at O, summation of moment at the point. For the example, let's say you have point B here at B. How to define this one? OGB. Basically, GOB nothing to do with rotation. I mean, if you want to choose point G, yeah, just the point G. O, you want to choose point O, yes, that's point O. Means that to choose GOB, nothing with the point of rotation. But you have to know lah, the point of rotation is O. But you can choose any point along point O to point B. You can choose, for the example, summation of moment at point here. For the example, let's say this point X. You can choose summation of moment at point X. Okay, that's the things, and that's the first thing. Okay, you can choose any point to calculate the summation of moment. Okay, as long as it's lay, its lay is better. It's lay on the rigid body. You can choose point. For the example, point Y here. For the example, you can make it, and the summation of moment at point Y. Okay. For the case of summation of moment at G, G refer to center of gravity. For this case only, a summation of moment at G, the equation is equal to Ig times alpha. If you have G here, G refer to the center of gravity, it cannot be Ig alpha plus MD kuasa 2 alpha. No, you cannot make it like this. You have only this term only. Only this term. If you choose G, you have to remember. Okay? You have to remember this thing. Okay? Okay. How to find... Okay, another thing is, on the left-hand side, okay, is anything to do with FBD. The summation of moment on your left-hand side or left side is anything regarding to free body diagram. Okay, free body diagram. And your right-hand side, Ig alpha, is everything about right-hand side. Oh, sorry, about kinetic diagram. Okay, alpha, you have the component alpha there. Anything about alpha. Okay, anything about KD. I mean, you have to look on KD diagram and kinetic diagram. You have to know that. Anything G, everything or anything come from FBD on right hand side is come from kinetic diagram. If you have element of force here, for the example force here, you plus force, so it's wrong. It's okay. That's the first one. Okay, let's see. What is IG? IG is the mass moment of inertia for the rigid body when it's rotate at G. By referring to point G. For that, it means that in the table, oh, sorry, it means that, let's say this is a point G. You calculate the moment by assuming point G is fixed. You assume that point G is fixed. Let's say go to the next. Let's say this one. I draw again. This is G. This is point O. Okay. OY, OX. You have W here. Okay. And then you have external moment. Similar, similar case. You just, if you understand this one for figure 1, you understand for the figure 2 you can make it by yourself. Okay, if you choose that summation of moment G is Ig alpha, it means that you assume point G is fixed. Point G is fixed. What happened is point G is fixed means that you have this FBD, FBD. So on your left hand side is everything about the FBD. Okay, we have moment here, external moment. So counterclockwise is positive values. Okay, counterclockwise is positive values. Uh, you have what? If you choose, okay, let's start with OX. OX here, you see that OX is goes toward point G. So OX is not counted for calculate the moment. Try to imagine that point G is fixed. You push it to the you push it by a force. We call it force X. Sorry, force OX. What happened to this system? This rigid body, does it move? Make it a single like this. You have G here, and then you have OX here. So you push this body through point G. Do you think that this rigid body rotate? Because you push it in line with G, it doesn't rotate. It doesn't create a moment. It doesn't create moment for this rigid body so that it can rotate. No. Okay, so that's why OX is not counted. How about OY? You fix O. You fix XG. You ignore other forces first lah. Try to imagine that you push it to the top. You fix point G and you push it to the top. What you can imagine, so that if you push it up to the top, so this one tend to rotate, correct? So it will create the moment. So you have OY time the radius from G to O, and the length is R R R. Oh, I put it as R. It's now. Yeah, R. 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 And then you have, how about G? How about G? G, if I draw G, sorry, how about W? W. If I draw W alone, I pull it down. What happened to this rigid body? It will rotate or not? No, it just goes down because this W line with point G, it doesn't create a moment. It doesn't make this rigid body rotates. So W is zero lah. It's not counted for calculating the moment. How about external moment? You have a 60 Newton meter here. So this one is given to you. It will create a counterclockwise moment. So it gives you, so OY is negative. Sorry, this one is negative. This one moment is positive because it's clockwise, counterclockwise. And then how to find the IG alpha? IG, you go to, if I still have here. Okay, if you go here, you see that G is in the middle, of course. This is a point G. It's rotate like this. You can imagine that it's rotate like this. You can see here it's rotate like this. So this I is referring to this motion. This is IG lah, for example. So it gives you 1/12 ml square. M is the mass, L is the length. The length of the road. So this is the IG. So it's similar to this. So it's similar by assuming that it's rotate at G. Okay, so IG, because you are calculating the moment when G is fixed. When G is fixed, it's rotate at G, for example. So 1/12 ml square. That the answers for first figures. First figures we have 0 OY times R plus W 1/12 ml square, because you can find it Ig. You can find it Ig in the figures. Okay, can figure Ig. Okay, for the second figure, first figure, second figure. If you can recall the uh, the free body diagram, it will give you these answers. 0, 1, see, because your G here, you can imagine times R. I put a R1 lah to differentiate between the radius in the figure 1 and figure 2. Figure 1 I put R, figure 2 I put R1 lah, and plus W. Okay, and it give you Ig alpha. So Ig immediately similar to this one, Ig, which is 1/12 ml square. Okay, similar. So this I forget to put alpha here. It's similar. Why? Okay, sorry, it's similar because you have the pin or x or y, you have pin or x or y, you have external moment 60 Newton, 60 Newton meters, and you have the same omega here, 6 radian per second. Okay, so it will give you the same answers, negative OY kali R, similar OIR, but the thing is R is different. R1 here and R here is different. Okay, but the equation basically similar. Okay, instead of use the M summation of moment at G, remember when summation of moment at G, it must be you have a single equation on single term of equation on your right hand side, Ig times alpha. Okay, sir, sometime I found that how to use the summation of moment at O for the example. We still have IO alpha. Yes, you have this equation. This equation is valid. Now, for the example, as I said just now, you can use the summation of moment at any point. For the example, we choose point O. So we choose point O. The summation of moment at O is IO alpha. Correct? IO alpha. Okay. For case number one, IO alpha, we have now you choose point O as your reference. So it's fixed. You want to create a moment when O is fixed. When O is fixed. Okay. You have what? You have OY, OX is not counted lah. You have W here. Okay. You have external moment. Okay. You have what? You have external moment is positive. Okay, counterclockwise. You have W downward, it will create a clockwise, so it will give you negative. So negative W times the radius. G to O is R. Okay. And IO is the mass moment of inertia of this figure or of this rod when it's rotate at O. O is at the end. Okay. If you see this one, you have G in the middle. This is the end, either one lah, or this one or this one. This moment of inertia stable give you the mass moment of inertia when the slender rod rotate at this axis. This is the axis. You can imagine how does it rotate. Okay, and then it give you, let's say this point O, IO is 1/3 ml square. You can use immediately, directly 1/3 ml square, but don't forget to put the alpha. Okay. So on how about right hand side? I mean the second figure. Okay, the second figure. O is not in the O is not at the end, not at the end of the cylinder rod. How we are going to calculate it? So if you see the figure, if you see the figure, it just give you only the mass moment of inertia when it's rotate in the middle or it's rotate at the end. For the example, if I draw it here, how about if it's rotate somewhere here? You have only in the figure you have only this one, this one and this one. But how if it's rotating somewhere here at this point? One not one third, one four from this distance from this end. Hmm? How? So we cannot. There's no equation given. What you have to do is you have to use the parallel axis theorem. Parallel axis theorem says that summation of moment at O. Let's say choose the counterclockwise positive is equal to Ig times alpha, of course times alpha lah, plus md square times alpha. Okay, d is what? D is the distance from G to O. Because you put G to O. G to O. G to O here I put the R1 just now. So you have to know that what is Ig? Ig is what? Ig is 1 over 12 ml square. Ig 1 over 12 ml square. Put in bracket. I put alpha outside. Plus m. D from G to O is R1. R1 square times that the mass moment of summation mass moment of inertia for figure number 2. Okay. Okay, some will say that is it possible, sir, to use for the figure 1 we use the parallel axis theorem? System, yes, you can use it. Yes. Okay, yes. But same concept of the second figure. Same concept as we have discussed in figure 2. Summation of moment at O counterclockwise is positive is equal to, let's say you want to choose IO alpha. Okay, and then this one similar, m minus omega times r. IO is Ig alpha plus m d G to O alpha. Okay, what is Ig? Similar, Ig doesn't change. Ig is 1 over 12 ml square. Okay, plus m R1. Sorry, this one is R1. This one is R. I put R. R square times alpha. This similar? Not yet. What you have to do is we know the R. R for this case number 1, R is L over 2. R from G to O is L over 2. Half. So 1 over 12 ml square plus m L over 2. L over 2 is L over 2 square times alpha. You can simplify this one. You can simplify this one because you will get 12 ml square plus 1 over 4 ml square alpha. Finally, you will get similar to this 1 over 3 ml square alpha. Similar. Okay, similar. So we have done for uh when you found, see, you want to use summation of moment at O, at the point of rotation. All right. Some ask me, sir, sometimes we found this kind of equation, uh, summation of moment. Similar, they use at O, sir. But I see that you put the IG plus MATR. So it make me confused. Sometimes I O alpha, sometimes I found these equations. How to do that, sir? All right. First, it's similar answers. If you use this one, it will give you the similar answers. All right. Summation of moment. Let's say you choose point O. We have discussed just now. You can choose like this lah, as I explained here. Okay. Summation of moment is equal to, yeah, sorry, before that, you come across this equation in some textbook, but before they come up with this equation or other some sort of this equation, you have to know that there is a one theory says that you can choose the summation of moment at any point. For the example, point O is equal the summation of moment due to the kinetic element at point O, or point O, point B, whatever point lah. Alright. So how to write this one? This one, you can see that this one is anything from FBD, similar to the previous one. This one also similar to the previous one, where you have to refer to the kinetic diagram. Okay, so let's start. I use a new page. Summation of moment at O is equal to the summation of moment due to the of the kinetic element at O. Okay, so similar to the previous case lah. Summation of moment at O. So you have what? We have M minus W times R. M minus W times R. This is your G. This is W. This is OY. This is OX. We have external moment. Okay. Okay. On the summation of moment due to the kinetic at O, you have to refer to to the kinetic diagram. We have written, we have drew in the first page. You have what? You have AT, you have AN, and then you have alpha. These three elements should be included. These three elements, AN, AT, and alpha, have to be considered on the right hand side of your equation. So you have alpha. Alpha, if you for the element alpha, it must come with Ig. So if you have alpha, it must be come with Ig alpha. That's the first one. Okay. How about AT element? AT, this is the point. AT create a counterclockwise moment. Counterclockwise. So it will give you positive value. So we know that moment, this is moment. The summation of moment. Moment is apa? Moment is F kali R. F apa? F adalah M kali A. M kali, sorry, F is mass times A times R. So means that for AT element you have M times AT, you got force, times R, radius from point G to point O. Okay, and then we know what is again, sorry, then what is AN? AN, you see that AN goes toward point O. So when it goes to a point O, AN is not counted in calculating the moment. Basically, in all cases, AN is not counted. Eh? Uh, so I leave it as 0 lah. So here, what is IG? IG is, if you go to previous one, 1 over 12 ml square. Okay, 1 over 12 ml square times alpha plus, what is M? M is M mass AT. AT is R alpha. Okay, R alpha, okay, times, so you will have 1 over 12 ml square alpha plus m r square alpha. Okay, easy. Easy, okay. For the second figure, you see that summation of moment due to the at O equal to the summation of moment of the kinetic element at O. Similar things, similar thing, I think similar. You have m minus w times r1, this is G, r1, okay, equal to ig, sorry, ig alpha. So when alpha elements here, sorry, I draw it here, at an, this is a point O, and then you have alpha. So when the element alpha must come together with ig, remember, so ig times alpha plus at, similar, m at times r1. R1 means that from point G to O. So AN is not counted lah. So what left is IG 1 over 12 ml square alpha. Okay. Plus mr square r1 square alpha. Okay. So you can simplify this one until you get that 1 over 12 ml square alpha plus because R1, sorry, R1 is what? Oh, sorry, you can simplify this one. So you will get that 1 over 12 ml square plus mr1 square times. So here you can simplify. Sorry, here, this one you can simplify to, if I'm not mistaken, 1 over 3 ml square times alpha. You can see that this answers similar to what you have found before. 1 over 3 ml square alpha. Okay, so I think that's the explanation of how to use the summation of moment. Sometimes you comes across the IG I know summation of moment due to the of the kinetic element at point O, and so on and so forth. Alright guys, I have discussed this one for 45 minutes. 45 minutes is too long lah. Try to understand the whole uh, 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 lectures, and then try to solve the problems. In this problem, you have to find uh, in this problem you have to find um, um, in this problem we have to um, find OX, OY, and alpha. Okay, so I highlight in black, black for both cases. For both cases, have to use this one, similar to this one. I put here as this one 1 2, this one AB. Okay, okay, we have three equation, right? Try to use this one for case 1, this one for case 3, sorry, case 2. So 1 2 3, let's solve it using this one, these three equation, and what is the answers for figure 2, A B C. Okay, then use the equation number 1, number 2, number 1, number 2, and number 4, and find the answers. Either you get the wrong, if you get different answers, something wrong with your calculation. A B C, sorry, use A B and D equation to solve it. Okay, and use equation number 1, number 2, and number 5 here. Number 1, number 2, and number 5. Try to solve it. This one, solve using equation A, B, and E. Okay? That means that you have to try combination of equation 1, 2, 3. 1, 2, 4. 1, 2, 5. Case number 1. Number 2, A, B, C, A, B, D, and A, B, E. Alright. One thing is, I want you to find, let's say this is a point B. Find the moment at point B. At point B. Okay? And you use this one. You can take. So this equation I put as equation number 6 for case 1. F for figure 2, case 2. So another task or another exercise. 1, 2, 6, and A, B, F. Try to solve it, class. So I think this video has clearly explained how to use the mass moment of inertia. So anything, just let me know if you still have problems, so we can discuss in detail later on. Maybe just personally we discuss it personally. Thank you very much for your times. Hopefully enjoy your days. So anything, just let me know. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.